Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to be exploring the forces which are generated on a moving charge. Now the key thing to understand is that if we've got a moving charge which is flowing through a magnetic field, we stated right at the beginning of this unit that if a charge moves it also generates a magnetic field. So a single charge moving through a magnetic field will have two fields interacting. We've got the magnetic stationary field and then we've got the magnetic field which is generated by that moving charge. As a result, a force will be generated due to this interaction. Now we can determine the direction of this force using the slap rule. Now in this case we know that we've got two different types of charges. We've got positive and negative charges. Now as you're probably aware at this level, initially they thought that the charges of electrons were going to be positive. It wasn't until Millikan's experiment where it was determined that it was actually negative. Now as a result we're going to have to do two different types of slap rules which are going to apply to two different types of charges. So basically what the way it works is as follows. If you want to deal with anything positive, you use your right hand slap rule, and that is the principle behind all of the reasons why we use the right hand slap rule when we're looking at the DC motor or when we were looking at a current carrying wire. For a negative charge, we always use our left hand rule. Now let's just recap on what the slap rules work on. So there's my hand, and basically this is how it works. The thumb in this case is going to be the movement or the direction of movement of the charge. The fingers are going to point in the static direction of the magnetic field of the magnet. And finally, the palm is going to be the force on the charge. So your thumb is going to be your movement of your charge, your fingers are the direction of the magnetic field, and your palm will be the force that's applied. Now, as I said, we've got two rules. If we're dealing with positive charges, we always use our right hand, and if we're dealing with negative charges, we always use our left hand. Please, please, please learn this when we're dealing with charges. When we're dealing with DC motors or the motor effect, you use your right hand rule and your right hand grip rule, and everything's right-handed. When we're dealing with charges, we've got two types of charges, negative and positive, so we use our left hand for negative, and our positive, we use our right hand. Okay, so let's see some of the observations that were seen with respect to different charges. So what I've got here is a negative charge which is entering a magnetic field. So if I've got a negative charge entering a magnetic field, we're going in this direction. So notice here I'm using my left hand. Now unfortunately it's going to be back to front because of the camera, but if you do this with me then hopefully it will make sense. So my direction of my negative charge is going from left to right. My magnetic field is moving into the page. The result is the force is pushing downwards. Now that force basically is going to be acting at 90 degrees, pushing it straight down. Now the resultant vector of this movement means that it generates a 45-degree angle. So what now happens is we've now got that field moving in this direction. We've then got our magnetic field going into the page. So the result is my force is going to push it round. So that as a result, I'm going to push my direction further down. Still going into the page, my force is now going to be acting at 90 degrees, and so forth and so on. And you will notice that in all of these cases, the forces going to be acting are perpendicular to the direction of the motion. But look what we've produced. Within that field, we've actually generated a circle. A circular motion has been generated if the magnetic field is big enough. Otherwise, what will happen is the electron will pass through the magnetic field and then just pass out. Now, if you think about that, that's the principle behind a cathode ray tube, where you actually had electrical charges, you had a beam of electrons coming through, and you had a fluorescent screen. And this is what used to happen with the TV screens, where the beam basically scrolled across the screen at an incredibly fast rate, controlled by magnetic fields. Put a magnet next to an old TV and what you will notice is you will change the direction of the beam. So we can generate a circular path if our magnetic field is big enough. So what things do we need to glean from this observation? Well, the first thing we need to understand is that force always acts perpendicular to the charge motion, and it will deflect it. So remember that we can be just deflecting it down, but if we have a big enough field and the charge is moving fast enough within that field to get into that field and then be subjected to those forces, it will produce a circular path. So that deals with a negative charge. Well, a positive charge is just going to be the opposite. So let's have a look. So in this case, I'm going to use my right hand because I'm dealing with a positive charge. I notice that it's going from left to right again. My magnetic field is going in. So using the laws that we've just looked at, the force should be acting straight up. Okay, as a result, that's the direction of the new vector. So I go up, field going in, pushing to the side, and the result is I get a perpendicular force which is generated. The result is it produces a new direction. Same thing, up, in, force, right to left, and so forth, and so on, until eventually I'm going to generate a full circle. And again, the force always acts perpendicular to the charge motion, and the result is it can produce a circular path. So if it now produces a circular path, we must be able to find an algorithm which is going to allow us to actually calculate those forces which are generated. So we know that the size of the force obviously is going to be determined by the charge, the size of the charge. Obviously, the bigger the charge which is moving, the more magnetic field it's going to generate. Remember, the magnetic field of the stationary magnet is the same, it's constant, so the interaction will increase with a larger charge. If the speed of the charge increases, just like we have with current, the result is we also generate a larger magnetic field. And finally, we can increase the magnetic field's strength, i.e. B, and if we increase that, then the result is we're going to get greater interaction. Now, as we found before, we know that force can be determined by F equals BIL, or BIL sine theta. Obviously, it's BIL if theta equals 90 degrees. So the force will equal the field strength times the current times the length of the wire. Well, in this case, we don't have a length. So we do have current. We do have a charge. We're not dealing with current. Now, we know that current is basically the charge over the time, the rate at which charge is flowing at a specific point. So we can substitute in for I, so that instead of I, we get a formula now, which is force equals the field strength times the charge Q times the length of the wire over the time taken. Now, as I stated, we don't have a wire in this case, we just have a moving charge. But hang on a second, we know that length is a distance, and t obviously is time. We've got distance over time. So if we've got distance over time, that's the same as velocity. So as a result, we can get the formula F equals the field strength times the charge times the velocity. Now, obviously, we're going to be working at, if it's going to be working at 90 degrees, we've obviously got, if it's less than 90 degrees, we've got BQV sine theta. If it's at 90 degrees, so they're going in the same direction, the result is that theta is going to be 90 and it equals 1, hence that's where we get the BQV. Okay, so I hope that makes sense. So what else can we do? Well, we can convert it into the circular motion. Now we know that circular motion, as you can see from the blue ellipse, the force generated there is the mass times the velocity squared over r. But we can substitute in for the force here, because we know for a charged particle, the force generated on a charged particle is BQV from the green ellipse. So if we substitute in the force from the green ellipse into the force for the blue ellipse, we then get our purple ellipse, which is basically BQV equals mv squared over r. But we know we can cancel out v on both sides and swap them over so that we can work out the radius of the circle which is going to be generated if we were able to allow our charge to actually pass all the way through. So as a result, we get an overall formula which is shown in the red ellipse. R equals the mass times the velocity divided by the magnetic field strength times the charge, where R is going to be the radius of the circle which is generated inside the magnetic field by the charge in meters. Now we know that the circumference of a circle is 2 pi r, so as a result we can also have substitute in V equals 2 pi r over t, where t is going to be the time period of the circle. So we've got a variety of different things that we can work on with respect to charge floating into a magnetic field. And if you go and try some of the exercises that I've posted, I put a worksheet on this post, then you'll be able to see the different types of questions that you could be asked. So let's have a look at a quick question here. Now here we've got a diagram where you can see we've got a proton, basically which is moving into a magnetic field, and the result is that as it moves in, it doesn't produce a full circle, but basically it's being diverted into its final path. It says in the diagram opposite, the charged particles are protons of mass 1.67 times 10 to the negative 27 kilograms. They enter a magnetic field of strength 3 times 10 to the negative 2 Tesla at a velocity of 2.5 times 10 to the 5 meters per second. We've got to determine the force acting on the protons and the radius of curvature of their path in the field. So what is it? How is it deflected? So let's look at the first situation. So in this case, the first situation, we know the charge of our proton, because it states under the diagram, is 1.6 times 10 to the negative 19 coulombs. We know the mass of our proton. The force basically will be utilized using BQV. So the force equals BQV. We know that B is going to be 3 times 10 to the negative 2 Tesla. We know that Q is going to be the charge, which is 1.6 times 10 to the negative 19. And we know the velocity is 2.5 times 10 to the 5. So the result is that our force generated on our proton basically is going to be 1.2 times 10 to the negative 15 newtons, and it's going to be upwards. Remember, we're dealing with a proton, so it's moving upwards. You can see in the diagram it shows electrons. This is literally just a diagram I took. I wasn't able to get one with protons on it. So it's pushing straight upwards in this case. Now, what else do we get? Well, we can see that the radius of the curvature of their path in the field, so to work out the radius, we're going to be using the algorithm that we ran through earlier, which is mv over bq. So we know what the mass is from the question, we know what the velocity is from the question, we know what b is from the question, and we also know what q is from the question. So it's a simple calculation, and we get 8.7 times 10 to the negative 2 meters. Okay, well, I hope you found that useful. So when we're looking at different charged particles, the classic question that you often get is charged particles with respect to radioactive substances, where you're using a beta particle and an alpha particle. If you remember, beta particles are always positive, alpha particles are always negative. Gamma particles have no charge, so they're unaffected by a magnetic field. And the result is you can use your right or left-hand slat rule to determine which one is going in which direction. Okay, well, thank you for joining me, and I hope to see you again.